Hi everyone, welcome back to the channel. Thank you so much for tuning in to another deep dive into Earth's forgotten histories. If you enjoy this kind of calm science storytelling, please remember to like the video, subscribe and share it with someone who loves mysteries about our planet. Before we begin, I'm really curious, what time is it where you are right now and where are you watching from? Let me know in the comments below. Alright, settle in and let's explore the era when Earth almost never stopped flooding. In the late Triassic, long before familiar continents drift into their present positions, the surface of Earth is dominated by a single immense landmass. This supercontinent, known as Pangaea, stretches from high northern latitudes deep into the south and covers roughly 1/3 of the planet. Around it lies a vast global ocean often called Panthalassa, while a smaller seaway, the Paleotethys, occupies the gap between the great landmass and scattered island arcs. From distance, the pattern appears simple: one continent, one ocean, clear boundaries. At ground level, the simplicity disappears. The interiors of Pangaea lie far from any coast. Moist air from the surrounding ocean loses most of its water long before reaching these central regions, leaving much of the interior locked in arid and semi-arid climates. Wind drives broad systems of sand dunes that move slowly across basins. Exposed bedrock weathers under a hot sun breaks into rubble and accumulates as alluvial fans at the feet of long mountain fronts. Lakes and rivers exist, but many are seasonal or short-lived. Only narrow belts along coasts and some highland regions, where air is forced to rise and cool, support more stable humidity and more continuous vegetation. This world has already experienced a catastrophic transition. Tens of millions of years earlier, near the boundary between the Permian and the Triassic, volcanic activity and related feedbacks drove the largest known mass extinction in the geological record. More than 4 out of every 5 marine species and a large fraction of land species disappeared. The biosphere has been rebuilding ever since. By the time of the Carnian stage, which occupies a slice of time in the early part of the late Triassic, new groups of organisms have become established. Reptiles with upright limbs and efficient breathing begin to explore roles that older lineages once held. Early relatives of mammals persist in scattered refuges. Conifers, seed ferns and other plants form patchy forests in areas where soil and rainfall allow them to take hold. The atmosphere and oceans also bear the marks of this long recovery. With much of the carbon that once cycled through the biosphere locked away in buried sediments and altered rocks, background climate settles into a generally warm but somewhat stable state. There are strong temperature contrasts between the equator and the poles, yet polar regions remain free of permanent ice. Seasonal changes in sunlight and temperature drive wind patterns that in turn drive large-scale circulation in the global ocean. Over the supercontinent, this circulation expresses itself through monsoonal systems. In a monsoon regime, land and sea heat at different rates through the year. During warm seasons, the land surface rises to higher temperatures than the adjacent ocean. Air above the land becomes buoyant and ascends, drawing in moist air from over the sea. As this moist air moves inland and rises further over elevated terrain, its water vapor condenses into clouds and falls as rain. During cool seasons, the contrast reverses and winds drive dry air outward toward the sea. On a typical continent, this pattern generates distinct wet and dry periods. On Pangaea, with its vast interior and long coastlines, the effect is amplified. Geological evidence indicates that much of the low-latitude belt experiences what some researchers describe as mega-monsoons, with seasonal rainfall far more intense and spatially extensive than in most modern monsoon systems. Sedimentary rocks deposited along ancient river plains and coastal lowlands preserve this rhythm. Stacked layers of sandstone and mudstone show repeating alternations between river-dominated and soil, forming intervals suggesting cycles of flooding followed by drying. Mud cracks and wind-blown sand beds record episodes when surfaces fall dry enough for desiccation and transport by air. Other horizons contain plant roots, coal, rich layers, and traces of standing water reflecting wetter phases. Together, these archives outline a climate in which the passage of time is measured not only in years but in swings between extremes. Despite these harsh swings, life spreads into many niches. Along coastal margins where moisture is more reliable, forests of conifers and broad-leaved seed ferns create layered habitats. Ferns and horsetails occupy understories and the margins of streams. In these environments, early dinosaurs, still small and lightly built, run on two legs between tree trunks, sharing space with a wide variety of reptilian and synapsid forms. Some lineages resemble later crocodiles but live on land and fill the roles of medium and large predators. Others are herbivores, with barrel-shaped bodies adapted to processing tough plant material. Small insect-eating animals move through the leaf litter, leaving only occasional bones and burrows as evidence of their existence. Inland, away from the relative refuge of coasts, conditions remain more severe. Central Pangaea hosts some of the driest environments known from the entire Triassic. Mountain ranges near the centre of the continent cast extensive rain shadows. Moist air masses that approach from the oceans are forced upward, release much of their water on windward slopes and descend toward the interior as hot, dry winds. These processes maintain deserts with dune fields that may reach hundreds of kilometers in width. Fossil assemblages from such regions are sparse, often limited to hardy plants and animals able to tolerate high temperatures and prolonged lack of surface water. To reconstruct this world, modern scientists rely on lines of evidence that converge from many directions. Fossil bones and teeth reveal which kinds of vertebrates are present in particular formations. Pollen and spores preserved in shales and fine-grained sandstones show which plant groups dominate local landscapes. Geochemical signatures in carbonates and organic matter hint at average temperatures, rainfall patterns, and the composition of the ancient atmosphere. Magnetic minerals record the wandering of the magnetic poles and help to fix the positions of continents through time. From these data, a coherent picture emerges of an Earth system that, while dynamic, does not yet show signs of widespread climatic chaos. Seasonal extremes are strong, but they follow repeatable patterns tied to astronomical cycles and continental geometry. There are storms and droughts, but the long-term averages remain within ranges that many organisms can tolerate. Yet some details within this picture already hint that the apparent stability may be conditional and temporary. The configuration of one supercontinent surrounded by one dominant ocean concentrates many feedbacks in a single coupled system. The same mountain chains that carve rain shadows also focus erosion and sediment transport into particular basins. The same monsoons that bring essential water to coastal lowlands also test the limits of soil stability and river capacity. Volcanically active regions at the edges of the continent periodically add new pulses of carbon dioxide and other gases to the atmosphere. Each process taken alone lies within a plausible range of variability. Taken together, they create a climate apparatus that is sensitive to disturbance. The late Triassic Earth stands at a point where evolution has produced diverse and increasingly complex ecosystems on land and in the sea, yet the physical framework that supports them is finely balanced. A modest additional push arriving from deep within the planet could be enough to shift this balance. In later rock layers preserved far above the ancient river plains and desert floors of Pangaea, signs of that push will appear as a sudden thickening of mud-rich deposits, as chemical departures in soil horizons, and as a new pattern in the distribution of fossils. Long after the rains themselves have ceased, and the supercontinent has broken apart, these clues will wait in silence for investigation. Before the new chapter begins, the planet occupies this state, warm, dry in many regions, pulsed by powerful but regular mega-monsoons filled with organisms still exploring post-extinction possibilities. It is a world that appears to have regained its balance even as slow processes beneath the crust assemble the conditions for an era in which water will fall more often than it holds back. In the present, long after the supercontinent has broken apart and its pieces have drifted to their current positions, the story of the Carnian pluvial episode is reconstructed from rock. There are no written records from that time, no direct measurements of rainfall or temperature. Instead, there are cliff faces, drill cores, and scattered outcrops on several continents. Each one preserves a local history of deposition and erosion. Taken together, these records allow a picture to form of an interval when ordinary climatic rhythms gave way to something more prolonged and unusual. The most basic evidence lies in the character of sediments. Layers that were once horizontal rivers and floodplains are now tilted and exposed, sliced open by more recent erosion. In many late Triassic successions, geologists find repeated patterns, reddish mudstones, that formed in well-drained soils overlain by thicker, darker packages of fine-grained material, rich in organic matter. Within these darker intervals, features of intense surface runoff appear. Channels cut downward into older beds, and are later infilled by coarse debris. Slopes are mantled with chaotic breccias, a mixture of rock fragments and soil, transported by rapid flows of water. In some regions, these erosion surfaces extend across large distances, suggesting that the processes that created them were not small local storms but widespread events. When these observations are organized by age using fossils and radiometric dates from volcanic ash layers, they tend to cluster around the same slice of time, the Carnian stage. In several basins, the shift from predominantly red oxidized sediments to more grey and brown waterlogged deposits is abrupt. This transition is not unique to one continent. Similar changes are seen in outcrops now in Europe, in parts of modern North and South America, and in scattered sites elsewhere. The distribution hints at a driver that acted on a global scale rather than a local tectonic or climatic fluctuation. Soil layers or paleosols provide further detail. Ancient soils retain structures that reflect their formation environment. Under moderate rainfall, soils tend to develop distinct horizons with iron oxides and other minerals forming characteristic bands. Under very high rainfall, soil horizons can become thicker, with more intense leaching of soluble components. In Carnian paleosols associated with the suspected pluvial interval, geologists describe features consistent with prolonged wet conditions. Some profiles show strong evidence of water saturation, such as the presence of slickensides and glade horizons which form when iron is repeatedly reduced and oxidized under fluctuating water tables. Others host abundant nodules of minerals that precipitate when groundwater moves through soil for extended periods. When these paleosols are compared with modern soil analogues formed under tropical or subtropical humid climates, the similarities are notable. This suggests that parts of Pangaea once experienced levels of moisture more commonly associated with present-day rainforests or monsoon forests than with arid continental interiors. A more specific indicator comes from small, often overlooked inclusions in these ancient soils and sediments, amber and other fossil resins. Resin is produced by many trees as a response to injury or stress, and in humid environments where decomposition is normally rapid resin that becomes buried quickly, can harden and preserve microscopic bubbles of ancient air as well as traces of plant and insect material. In some Carnian sequences, there are unusual concentrations of resin-rich layers associated with the wetter deposits. Their abundance suggests that resin-producing vegetation was widespread and that conditions favoured the preservation of this material. The presence of amber in soils that formed under high rainfall supports the idea that forests expanded and became more continuous during this interval, consistent with other traces of increased plant cover, such as coal seams and dense root networks. Another line of evidence comes from the degree of erosion recorded by bedrock exposures. In certain regions, surfaces cut during the Carnian pluvial episode reach down into what geologists describe as basement rock, older crystalline rocks that normally lie beneath many hundreds or thousands of meters of younger sediments. To bring such rocks to the surface requires a significant amount of material to be removed, while tectonic uplift can raise blocks of crust. The removal of overlying sediment is achieved mainly by water, and in some cases ice. In the late Triassic, there is no sign of extensive glaciation, so liquid water is the primary agent. The depth and continuity of these erosional surfaces imply that rainfall and runoff were capable of stripping away thick sequences of cover more efficiently than in preceding and following intervals. This is compatible with a scenario in which precipitation not only increased, but did so for long enough that landscapes could be reshaped on a large scale. Geochemical markers add another dimension. Ratios of stable isotopes of oxygen and carbon in carbonate minerals, as well as in organic matter, can reflect changes in temperature, rainfall, and the balance between different sources of carbon. During the Carnian, many records show shifts consistent with warming and with an accelerated hydrological cycle. Oxygen isotope values in marine carbonates suggest higher sea surface temperatures and potentially altered patterns of evaporation and precipitation. On land, changes in carbon isotopes from soil carbonates and plant remains indicate pulses of carbon entering the atmosphere and ocean system, likely from volcanic outgassing, and possibly from the destabilization of methane-rich deposits. These changes align in time with the sedimentary and paleosol evidence for increased rainfall, pointing toward a coupled climate and carbon perturbation rather than isolated local anomalies. Fossil assemblages from the same interval provide biological context. In some marine sections, groups of organisms that build shells and skeletons from calcium carbonate decline or disappear, while others that tolerate lower carbonate saturation or change salinity appear or increase. On land, community composition in plant fossils and vertebrate faunas shifts across the suspected pluvial boundary. Some herbivorous groups that were abundant in earlier Carnian formations become rare or absent, while other lineages expand their range. These biological turnovers do not match the abrupt near-total losses seen at the largest mass extinctions, but they do point to elevated extinction rates and rapid ecological reorganization. The timing again coincides with the interval of unusual sedimentation and geochemical anomalies. When all of these observations are plotted together on a time axis, a pattern emerges. There is a period of relative stability in the early Carnian, with sedimentary geochemical and biological indicators fluctuating within modest bounds. Then, within a relatively short geological time span, there is a coordinated shift. Warmer conditions, more humid soil signatures, increased evidence of powerful runoff, and deep erosion reorganized ecosystems. After this interval, some parameters return toward previous values, while others, such as the composition of dominant vertebrate groups and plant communities, do not. The system has been moved to a new state. At first, this pattern could be interpreted as a series of unrelated local changes, each driven by regional processes. A single basin might have experienced uplift and increased rainfall due to changes in nearby topography. Another region might have undergone a local marine transgression driven by crustal subsidence. However, as more sites are studied and more precise dates are obtained, the coincidence of similar signatures at similar times in widely separated locations becomes harder to dismiss as chance. The idea of a distinct Carnian pluvial episode takes shape a globally significant interval of increased rainfall, humidity, and associated environmental change that persists for perhaps 1 to 2 million years. Even with this framework, uncertainties remain. The exact duration of the wettest phases, the spatial extent of the most intense rainfall, and the detailed sequence of events differ slightly from record to record. Some proxies respond more to temperature than to rainfall, others to local conditions more than to global drivers. There's also the question of mechanism. What process or combination of processes could have altered the hydrological cycle on such a scale and then allowed it to relax again? The sediments and soils show what happened at the surface. The isotopes hint at changes in temperature and carbon cycling. Fossils chronicle who survived, who declined, and who diversified. To understand why the rain intensified and why it eventually eased attention turns to the sources of heat and gas that lie beneath the crust. The search for their fingerprints leads to volcanic provinces that were active during the Carnian, where immense outpourings of basaltic lava testify to deeper disturbances in the mantle. In those flood basalts, investigators suspect the missing link between gentle monsoon rhythms and an era of almost continuous flooding may be found. The link between the Carnian pluvial episode and the deeper behaviour of the climate begins with the geometry of Pangaea itself. A supercontinent this large alters the way air moves around the planet. Over an ocean, water moderates temperature. Over rock and soil, temperature responds more directly to sunlight. In the late Triassic, the broad interior of Pangaea heats strongly in warm seasons and cools more rapidly when sunlight weakens. This contrast between land and sea drives large-scale circulation cells that in turn organize winds and rainfall. In simple terms, warm air rises over the heated interior, and cooler air from over the oceans flows in to replace it. As that moist air moves inland and upward, it cools and releases water as rain. This is the basic monsoon pattern, but on Pangaea it is intensified by scale. The distance from coast to interior is so great that air masses can carry moisture deep into the continent once they're drawn in. The result is a system of what some researchers call mega-monsoons, seasonal cycles of circulation and rainfall that are stronger and more expansive than those seen on most modern continents. The details of this circulation depend on topography. Pangaea is not a flat slab. There are belts of mountains formed where plates collide, and there are uplifted regions above deep-seated magmatic anomalies. Central Pangaea hosts a significant highland chain that runs roughly east to west. When moist air is carried inland during the monsoon, this mountain belt forces it to rise sharply. On the windward side, clouds thicken, and rainfall increases, feeding rivers that descend toward lower plains. On the leeward side, descending air becomes warmer and drier, casting large rain shadows over interior basins. Sedimentary records from these different settings show the contrast. Windward slopes and adjacent fallen basins host thicker packages of fluvial sediments with evidence of repeated flooding. Leeward areas preserve more windblown deposits and evaporate layers that form where shallow lakes frequently dry out. Even in the absence of any unusual external forcing, such a configuration creates a climate of strong regional contrasts and strong seasonality. To understand why this system might tip into a much wetter state, it is useful to consider how the global water cycle responds to changes in temperature. When air warms, its capacity to hold water vapor increases. For every small increment of warming, the atmosphere can store more moisture before condensation occurs. This means that in a warmer world, monsoonal circulations have more water to work with. When air finally does rise and cool, the resulting rainfall events can become more intense. In addition, warmer oceans evaporate more water, adding to the flux of moisture into the atmosphere. The speed of the hydrological cycle increases. Water evaporates more readily, moves more quickly through the atmosphere, and falls more often and more heavily as rain or snow. In modern climate studies, this relationship is observed as a tendency for extreme rainfall events to become more frequent in a warming environment, even if the total number of rainy days changes less dramatically. In the late Triassic, when the background climate is already warm, any further addition of heat from greenhouse gases has the potential to accelerate the water cycle in this way. The geometry of Pangaea sets the stage for a strong response. With vast heated interiors and extensive warm marginal seas, any increase in atmospheric moisture can feed directly into the monsoon system. There is also a slower but important interaction between climate and the land surface. Over long timescales, climate influences rates of chemical weathering of rocks. Rainwater, slightly acidic because it contains dissolved carbon dioxide, reacts with minerals in exposed rock and soil. These reactions consume carbon dioxide and produce ions that eventually wash into the oceans and contribute to carbonate formation. When rainfall increases and temperatures rise, chemical weathering tends to speed up, increasing the drawdown of carbon dioxide. This process can act as a stabilizing feedback, gradually pulling atmospheric carbon levels downward after a warming pulse. On a supercontinent with large upland areas and broad river networks, this feedback can be powerful, but it operates over hundreds of thousands to millions of years. In contrast, the injection of greenhouse gases into the atmosphere from volcanic sources can occur over much shorter intervals. The balance between rapid volcanic input and slower weathering removal becomes a key control on climate. In the Triassic, this balance is periodically disturbed by large igneous provinces, vast regions where magma rises and erupts through the crust. Before considering a specific province linked to the Carnian pluvial episode, it is useful to note how such events affect climate in general. When flood basalts erupt, they release lava that covers large areas, but they also release gases, carbon dioxide, water, vapor sulfur species, and in some cases methane and other volatile compounds. Carbon dioxide and methane trap outgoing infrared radiation, warming the surface and lower atmosphere. Sulfur gases can form aerosols that reflect sunlight and initially cool the surface, but these aerosols are relatively short-lived compared with long-lived greenhouse gases. Thus, the climatic impact of a flood basalt sequence can involve a short period of complex cooling and warming signals, followed by a longer interval of elevated greenhouse forcing. If the eruptive phase is concentrated into a geologically brief period, the rate of greenhouse gas release can outpace the capacity of the oceans and active weathering to absorb it, causing a rapid rise in atmospheric carbon. For Pangaea, positioned as a large, mostly low-lying landmass, this kind of perturbation would likely amplify existing monsoon patterns. As greenhouse gases increase and temperatures climb, the hydrological cycle would speed up. Mega monsoons already delivering heavy seasonal rainfall could become more intense, with longer wet seasons and more frequent extreme events. The contrast between wet and dry regions might sharpen. Some areas could shift from semi-arid to humid regimes. Others might experience more concentrated and erosive storms despite similar annual rainfall totals. The central question is not whether more greenhouse gases would affect the Pangaean climate. Basic physics suggests that they would. The question is how this general expectation connects to the specific signatures seen in Carnian sediments, the switch to waterlogged soils in many regions, the evidence of deep erosion penetrating into basement rocks, and the changes in biotic communities. To address this, researchers look for volcanic provinces whose ages overlap with the Carnian and whose scale is large enough to influence the global carbon cycle. One of the most significant candidates occupies what is now part of Western North America. In the Triassic, this region lies along the margin of Pangaea facing the Panthalassa Ocean. Here, tectonic processes associated with subduction and mantle upwelling give rise to extensive basaltic volcanism. The resulting rock sequences, now exposed in mountain belts and plateaus, represent an ancient large igneous province. Their thickness, lateral extent, and chemical composition indicate that they formed during an interval of intense magmatic activity. Radiometric dating places the main eruptive phases near the time of the Carnian pluvial episode. The correspondence in time is suggestive, but by itself not conclusive. Other lines of evidence are therefore examined. For example, certain trace elements and isotopic ratios in these basalts can be compared with global geochemical signals in marine sediments to test whether the same volcanic gases likely entered the ocean atmosphere system. In several cases, correlations are found between the inferred timing of gas release from such volcanism and shifts in global carbon isotopes consistent with a large addition of isotopically light carbon, such as would be expected from a mixture of volcanic carbon dioxide and possibly methane released from destabilized sediments. When this framework is applied to the Carnian, a coherent scenario forms. A large igneous province along the Pangaean margin erupts over a relatively short geological interval. It emits substantial quantities of carbon dioxide and perhaps triggers the release of methane from shallow marine deposits. Atmospheric greenhouse forcing increases. Global temperatures rise by several degrees as oceans warm, evaporation intensifies. The atmosphere holds more moisture and delivers heavier precipitation when air ascends, particularly in the dynamic monsoon regions of Pangaea. The hydrological cycle accelerates, and in many basins the balance between soil formation and erosion shifts toward erosion. At first, this is a conceptual model, an organized way to link disparate observations. Over time, as more stratigraphic sections are studied and more precise dating is applied, the model gains support. Yet some aspects remain uncertain or only partially constrained. The exact amount of greenhouse gas released, the spatial distribution of temperature changes, and the feedbacks involving cloud cover and vegetation are difficult to reconstruct in detail. Numerical climate models which solve equations describing atmospheric and ocean circulation on simplified reconstructions of Triassic geography offer additional insight. When greenhouse gas concentrations are raised in such models for a world shaped like Pangaea, they often produce intensified monsoonal rainfall and expansion of humid zones into regions that were previously semi-arid. This behavior qualitatively matches the inferences from geological and paleontological data. The combination of theoretical understanding, model experiments, and field evidence strengthens the connection between supercontinent geometry, greenhouse forcing, and the emergence of a prolonged wet interval. The stage is thus set in two senses. In the ancient Triassic, magma collects at depth beneath the crust and prepares to surge upward. In the reconstructed understanding, information from many sources has converged to the point where an episode of unusual rain is no longer a vague idea, but a specific testable chapter in Earth history. What remains is to look closely at the volcanic event itself, the gases it likely released, and the precise ways in which those gases translated into almost continuous rainfall over parts of a supercontinent that had long been defined by dryness. In that connection between deep earth processes and surface water lies the core of the mystery. How for an interval counted in millions of years, the normal alternation between wet and dry seasons in many regions shifted toward a world in which flooding became a near constant presence. Deep within the Triassic mantle, long before any rain begins to fall on the surface, heat accumulates in zones where rock convects slowly upward. In one such region beneath the western margin of Pangaea, conditions cross a threshold. Solid mantle partially melts, producing basaltic magma that starts to rise. Some of it stalls in chambers within the crust, but a significant fraction reaches the surface, feeding eruptions over a broad region that modern geologists now group together as a large igneous province. In present geography, fragments of these rocks are preserved in parts of what are now western North America and adjacent areas. They form thick successions of dark basalt that can be traced across mountain ranges, islands, and coastal outcrops. Careful mapping shows that these flows once formed a more continuous plateau of lava, later broken and uplifted by tectonic events. Radiometric dating of minerals within the basalts using the decay of radioactive isotopes with known half-lives places the main eruptive episodes in the Carnian stage of the late Triassic. The ages align closely with the interval during which sediments and soils record an unusual shift toward wetter and warmer conditions. In the field, the eruptive products reveal the style of volcanism. Many flows are several tens of meters thick and extend laterally for many kilometers, indicating that lava emerged not only from isolated vents, but also from long fissures. Columnar jointing formed as thick flows cool and contract suggests that some lava ponds remained molten for long periods before solidifying. Interbedded with the flows are layers of volcanic ash and reworked material recording explosive episodes and erosion between eruptions. The total volume of basalt emplaced is large, comparable to that of other provinces that are known to correlate with major environmental changes in Earth history. The lava itself is one part of the story. The other part lies in the gases that accompanied it. When basaltic magma ascends, dissolved volatiles exsolve as pressure decreases, forming bubbles that can drive fountains of lava and ash. Measurements on modern volcanic gases and inclusions trapped in ancient minerals indicate that carbon dioxide, water vapour and sulfur-bearing compounds are abundant in such systems. In addition, if magma intrudes into sedimentary basins rich in organic matter, it can heat those sediments enough to release methane and other hydrocarbons. In the context of the Carnian province, it is likely that eruptions released many trillions of tons of carbon in gaseous form over the course of several 100,000 to perhaps a couple of million years. The exact rate and total amount are uncertain, but simple scaling from other provinces and from geochemical constraints suggests that the output was sufficient to alter the global carbon cycle. Evidence for this lies not only in the timing of the basalts, but in the behaviour of carbon isotopes in marine and terrestrial records. Carbon has two stable isotopes of interest for climate studies, a lighter and a heavier form. Organic matter and some methane sources tend to be relatively enriched in the lighter isotope. When large amounts of isotopically light carbon enter the atmosphere-ocean system, the global average carbon isotope ratio in carbonates and other deposits shifts in a characteristic direction. In sequences that span the Carnian pluvial episode precisely dated, carbonate layers show such a shift consistent with the addition of light carbon from volcanic and possibly methane sources. The magnitude and pattern of the shift imply not a single instantaneous pulse, but a series of injections over an interval that corresponds broadly to the main phase of flood basalt volcanism. Parallel changes in oxygen isotopes in marine shells and carbonates point to an increase in sea surface temperatures by several degrees. This pattern fits the expectation from greenhouse warming driven by elevated carbon dioxide, warmer oceans, more evaporation, and a more vigorous hydrological cycle. Yet the translation from these global signals to the specific experience of persistent rain on Pangaea is not completely straightforward. Climate models indicate that when carbon dioxide levels are raised in a Pangaea-like configuration, monsoonal rainfall intensifies and humid regions expand. However, the fossil and sedimentary data from the Carnian suggests not only stronger monsoons, but also the formation of long-lived lakes, widespread swampy lowlands and deeply incised erosion surfaces. The scale of erosion in some basins implies that heavy rainfall and runoff persisted for long enough to remove substantial thicknesses of rock, which requires more than a brief climatic perturbation. The basalts thus provide a plausible engine and extended but still geologically concentrated eruption sequence that injects greenhouse gases faster than they can be removed. The hydrological response amplified by the geometry of Pangaea yields a prolonged wet interval. There are, however, regional complexities that resist simple explanation. Not all areas become wetter. Some parts of interior Pangaea, especially those already in extreme rain shadows, may grow even drier. Sediment records from certain basins show continued or even enhanced aridity, with thicker evaporate deposits and persistent aeolian sandstones. This heterogeneity reflects the way atmospheric circulation redistributes moisture. When the overall system carries more water, regions of ascent can become very wet, while regions of descent may become more strongly dry. In the Carnian, this divergence appears in the geological record as a patchwork coastal and marginal basins, with thick wet phase deposits, interior deserts that remain deserts, and transitional zones that switch between regimes. The pattern itself becomes another clue about how the climate machine responded to volcanic forcing. Between lava flows, landscapes near the eruptive centres would have experienced their own dramatic changes. Fresh basalt surfaces initially shed water efficiently, with little soil to absorb rainfall. Runoff would have been rapid feeding floods in downstream valleys. Over time, however, basalt weathers chemically breaking down into clay-rich soils that can hold water and support vegetation. In a world already pushed toward higher temperatures and faster hydrological cycling, this transformation from bare rock to soil could have further enhanced regional humidity by enabling dense plant cover. Vegetation transpires water, returning it to the atmosphere and feeding local rainfall. Thus, the interplay between lava emplacement weathering and plant colonization adds another feedback loop to the evolving climate. Geologists and climate scientists examining the Carnian province also consider the vertical distribution of gas release. Some lava erupted subaerially directly into the air, allowing gases to vent into the atmosphere. Other magma may have intruded into shallow marine basins, releasing gas underwater. Submarine degassing can change local ocean chemistry and, if extensive enough, contribute to global changes in dissolved carbon and oxygen. In the Carnian, marine records show signs consistent with stress on organisms that build carbonate skeletons, such as a reduction in carbonate platform development and declines in certain shell-forming groups. Lower carbonate saturation and altered salinity due to increased freshwater input from rivers would both have contributed to these stresses. The pulses of basaltic activity also may have influenced the stability of methane-bearing compounds in marine sediments. Methane hydrates, crystalline structures in which methane is trapped within water ice, are stable under conditions of low temperature and high pressure. Warming of bottom waters or heating of sediments by intruding magma can destabilize these compounds, releasing methane. Methane is an especially potent greenhouse gas over short timescales. If even a fraction of the methane contained in continental margin sediments was released during or shortly after the peak of volcanism, it could have amplified the initial warming driven by carbon dioxide, pushing the climate further into a state favouring extreme rainfall. This possibility remains difficult to quantify exactly, but it offers a mechanism by which relatively modest volcanic carbon dioxide emissions could be magnified into a stronger climatic response. Despite this combination of plausible processes, some aspects of the Carnian pluvial episode remain puzzling. For instance, the interval of peak wetness inferred from terrestrial deposits appears to outlast the main eruptive phase of the province in some reconstructions. This raises the question of whether secondary feedback such as enhanced weathering and vegetation changes sustained altered climate patterns beyond the active gas release period. Another question concerns the internal variability of the pluvial episode. Geological and fossil records suggest that within the broader wet interval, there were fluctuations, pulses of especially intense rainfall and erosion, separated by somewhat calmer phases. These may correspond to individual eruptive pulses, to orbital variations in insolation, or to internal oscillations in the coupled ocean atmosphere system. Sorting out their relative roles requires dense sampling and high-resolution dating that is still in progress. In the background of these details is a larger conceptual point. The Triassic climate system that exists before the pluvial event is already shaped by the presence of a supercontinent and by the lingering effects of earlier extinctions. When a large igneous province suddenly adds a substantial load of greenhouse gases, the resulting response is not a simple uniform warming. It is a reorganization in which regions that were once marginal for life become newly favourable, while others lose their habitability. In the Carnian, the rain does not fall everywhere with the same intensity, but where it does, it imposes a prolonged experiment on soils, rivers, plants, and animals. Lava flows on the margin and rainstorms in the interior are linked phenomena, parts of a chain that runs from deep mantle, upwellings to the composition of lake waters and the tensile strength of tree trunks in saturated ground. The Rangelia style basalts, therefore, are more than static rock units in a stratigraphic column. They are signatures of a moment when Earth's deep and shallow processes align to produce a climate excursion that is neither as sudden nor as devastating as the greatest mass extinctions, yet still strong enough to alter evolutionary trajectories. The next step in the story follows the water itself as it responds to this new energy balance. With greenhouse gases elevated and circulation patterns intensified, the sky over many parts of Pangaea begins to behave differently. Wet seasons lengthen, dry seasons contract, and what were once isolated storms begin to merge into a near-continuous pattern of rainfall. From the perspective of the geological record, this is seen not as a storm-by-storm account, but as a distinct layer in which the language of rock changes from red, oxidized surfaces and intermittent streams to grey, fine-grained deposits laid down under constant wetness. The onset of the Carnian pluvial episode marks this change, the moment when the consequences of deep volcanic activity fully express themselves in the ordinary medium of rain. As greenhouse gases accumulate and the energy balance of the planet shifts, the response of the atmosphere over Pangaea becomes visible first in the timing and intensity of rain. The familiar pattern of mega monsoons is still present, but the contrast between wet and dry seasons begins to blur. In many low-latitude regions, the onset of the wet season arrives earlier, and its retreat is delayed. Rivers that once swelled and then shrank on a predictable schedule now remain bankfull for much longer portions of the year. Floodplains that used to dry and crack between floods remain saturated. In the sedimentary record, this transition appears as a change from stacked packages of channel sands separated by well-developed oxidized soils to thicker intervals of fine-grained deposits that show repeated signs of standing water. Roots penetrate deeply into these waterlogged layers, and the boundaries between individual flood events become harder to distinguish. In some basins, accumulations of plant material escape complete decay and compress into peat, marking the re-establishment of peat-forming wetlands on a scale not seen in earlier Triassic strata. At the surface, the experience of this climate would be one of persistent cloud cover and frequent rainfall. Moist air drawn in from the surrounding oceans encounters a continent that now returns water to the atmosphere more efficiently. Warm temperatures enhance evaporation from lakes, rivers, and wet soils. Dense vegetation that has expanded into regions once too dry for forests transpires additional moisture. This recycled water joins incoming marine moisture in a thickening column of humid air. When that air is forced upward over even modest topographic features, condensation occurs readily, triggering rain. The cycle of evaporation, condensation, and precipitation accelerates to the point where breaks in rainfall become shorter and less regular. Modern climate analogues such as certain tropical monsoon regions give a partial sense of this regime, but on Pangaea, the scale is larger and the duration of the wet phase is longer. One indicator of this sustained humidity is the nature of the soils that form beneath the expanding forests. Instead of thin, weakly developed profiles typical of semi-arid settings, many Carnian paleosols show thick, mottled horizons with features that point to repeated saturation and reduction of iron. In some, there are clear signs of fluctuating water tables such as alternating red and grey zones and structures created by the shrinking and swelling of clay minerals. These are the kinds of soils that today support dense, long-lived vegetation in humid climates. Combined with the evidence for widespread resin production and coal formation, they suggest that forests and swampy woodlands spread across large portions of the supercontinent during the pluvial episode. the geometry of surface water bodies also changes. Rivers respond to increased runoff by incising more deeply into bedrock, where slopes permit carving valleys and transporting larger volumes of sediment toward low-lying basins. In flatter regions, enhanced discharge leads to more frequent overbank flooding and the development of broad floodplains cut by multiple shifting channels, where basins are internally drained or subsiding sufficiently to accommodate extra water. Large lakes form. These lakes may reach sizes that in plan view rival modern inland seas. Their shorelines migrate as climate and tectonics interplay, but in many cases they persist for hundreds of thousands of years. The sediments that accumulate in their depths record a different expression of the wet climate-laminated mudstones laid down under relatively calm water, occasionally interrupted by coarser layers delivered by storms or flood surges entering the lake from tributary rivers. The chemistry of these lakes is sensitive to the balance between inflow evaporation and connection to the ocean. Under the influence of sustained rainfall and high runoff, many lakes freshen at least near the surface. This reduces salinity and can stratify the water column with fresher water overlying denser, more saline layers left from earlier drier times. Stratification can limit the mixing of oxygen into deep waters, creating low oxygen or anoxic conditions at depth. In such settings, organic matter that sinks to the bottom is more likely to escape full decomposition, contributing to organic-rich deposits. These in turn affect local carbon cycling, and may store a portion of the carbon that was moved through the atmosphere as carbon dioxide during the volcanic pulses. As the hydrological cycle speeds up, extreme precipitation events also become more common. Even against a background of frequent rain, there are episodes during which moisture-laden air masses converge and lift more strongly than usual. The resulting storms drop intense rainfall over large areas in short times. On slopes and in confined valleys, these downpours trigger debris flows and landslides, entraining rock and soil into dense, fast-moving mixtures that scour channels and spread out onto adjacent plains. The sedimentary signature of these events is preserved as thick, unstratified or poorly stratified beds, composed of angular clasts set in a muddy matrix, capping more orderly river deposits. The depth and continuity of erosion surfaces at the base of some of these units suggest that such extreme events were capable of stripping away previously accumulated sediments and even cutting into older, more resistant rocks. These features match the idea of a climate in which not only the average rain falls more often, but in which the tails of the rainfall distribution extend farther into extremes. Yet the wet interval is not spatially uniform. While many regions become more humid, some areas, especially in the most sheltered interiors of Pangaea, remain arid or even become more strongly dry. Atmospheric circulation patterns, responding to the altered temperature gradients, and enhanced latent heat transport reorganize the positions of high and low pressure systems. In some models of Pangaean climate under increased greenhouse forcing, subsiding air over certain interior zones intensifies suppressing cloud formation and precipitation there, while rising motion increases elsewhere. The geological record accords with this, showing continued growth of large dune fields and evaporitic deposits in specific basins, even as neighbouring regions transition to wetter regimes. This juxtaposition creates sharp environmental boundaries across relatively short distances, with wet forests abutting deserts in some areas and long chains of lakes marking the seams between climate zones. The lived consequences for ecosystems are significant. Plants adapted to aridity find their ranges compressed or fragmented where humidity increases. New plant communities composed of ferns, conifers and seed ferns exploit the more reliable water supply and spread along river corridors and around lakes. On floodplains, dense vegetation stabilizes some banks and bars, while elsewhere repeated flooding removes soil and uproots trees, favoring opportunistic species. animals adjust in ways that can be inferred from shifts in fossil assemblages. Amphibians that require standing water for reproduction likely find expanded habitat in the proliferating ponds, marshes, and lake margins. Semi-aquatic reptiles and early crocodile relatives have access to more continuous networks of waterways. Small terrestrial vertebrates navigate a landscape in which refugees are more numerous, but also more frequently disturbed by flooding. For large herbivores and predators, the restructured mosaic of forests, wetlands, and more limited open ground alters hunting and foraging strategies. An intriguing aspect of this reconstructed climate is the duration of the altered state. Geological estimates suggest that the Carnian wet interval may have lasted on the order of 1 to 2 million years. This is long enough for multiple generations of plants and animals to adapt, radiate, and in some cases become dependent on the new conditions. It is also long enough for geomorphic processes to carve new valleys, build new delta plains, and bury older surfaces under hundreds of meters of sediment. Yet it is short when compared with the lifespan of the supercontinent itself. From the perspective of plate tectonics, this episode is a transient fluctuation superimposed on a much slower background evolution. The return toward more arid conditions after the pluvial episode therefore represents not simply a minor oscillation, but a reversal of a substantial reorganization. Why the system eventually relaxes is partly understood. As chemical weathering catches up with volcanic carbon dioxide input, atmospheric carbon levels decline, reducing greenhouse forcing. Vegetation and soils adjust, and the hydrological cycle slows from its accelerated state. But there may also be internal thresholds in atmospheric circulation, and ocean heat content that once crossed in the warming phase must be crossed again in the cooling phase before previous patterns re-emerge. The precise timing and sequence of these crossovers are still topics of investigation. Another open question concerns the fine structure of the rainfall itself during the episode. Rock records have limited temporal resolution. They can show that conditions were generally wetter and that extreme events occurred more often, but they cannot easily reveal whether rain fell gently for many days at a time, whether it came mostly in violent storms separated by shorter dry intervals, or how often skies cleared. Climate models can explore scenarios, but without direct observations, some aspects remain speculative. It is possible that different regions experience different expressions of the wet state, with some enduring near continuous light to moderate rain, and others marked by sequences of intense storms. In all cases, however, the shared outcome is the same soils that rarely dry, completely rivers that carry more water and more sediment, and ecosystems that organize themselves around a more abundant and more persistent presence of surface water. The Carnian pluvial episode therefore stands as an example of how a change in one component of the Earth system, in this case volcanic gas output and greenhouse gas levels, can alter the behavior of another component, the hydrological cycle, in a way that is sustained, spatially varied, and capable of reshaping both landscapes and lineages. The next focus turns from the land to the sea, where this same reorganization of water and climate produces effects that are less obvious in shoreline rocks, but just as consequential for the trajectory of life. Beneath the surface of the oceans, shells' thin communities reorganize, and the chemistry of seawater adjusts to the new balance of freshwater input and carbon loading. The flooded world on land has a parallel in the altered world beneath the waves. As rain falls more often and more heavily over Pangaea, the immediate changes are on land, but the ultimate sink for much of that water and for much of the eroded material is the ocean. Rivers swollen by persistent precipitation carry larger loads of dissolved ions and suspended sediment into marginal seas and open basins. At the same time, volcanic gases entering the atmosphere dissolve into surface waters, altering their chemistry. The Carnian pluvial episode therefore imprints itself on the marine realm in ways that are less visually obvious in outcrop than dramatic erosion surfaces on land, but just as significant. The most direct record of marine conditions comes from carbonate platforms and basins that fringed Pangaea and the Paleotethys. Before the pluvial interval, many of these shelves support extensive carbonate-producing communities. Organisms such as calcareous algae, some types of foraminifera, and a range of invertebrates build skeletons and frameworks from calcium carbonate constructing reefs and broad banks. Between these structures, lime mud accumulates generated both by biological activity and by chemical precipitation. Stratigraphic sections through these platforms show thick laterally continuous successions of shallow water carbonates, often with faunas indicating warm, relatively clear and stable conditions. Across the interval corresponding to the Carnian pluvial episode, this pattern is disrupted in many regions. Instead of steady accumulation of platform carbonates, there are gaps, erosional surfaces or replacements, basilicoclastic sediments derived from the erosion of continental rocks. In some sections, carbonate deposition resumes later with different faunal assemblages. In others, it does not recover fully. This interruption is often referred to as a carbonate platform crisis. It reflects a combination of stressors acting on carbonate-producing systems, changes in seawater chemistry that make carbonate precipitation more difficult, increased input of terrigenous sediment that clouds the water and smothers growing surfaces, and perhaps altered sea level or storm regimes. Geochemical measurements in Carnian marine carbonates and shales provide clues to these stressors. One important parameter is the saturation state of seawater with respect to calcium carbonate. This depends on temperature pressure and the concentrations of dissolved calcium and carbonate ions. When volcanic carbon dioxide dissolves into the ocean, it forms carbonic acid, which can lower pH and reduce carbonate ion concentrations. Even modest shifts can make it harder for organisms to build and maintain carbonate skeletons, especially in shallow warm waters. At the same time, enhanced weathering on land delivers more calcium and bicarbonate ions to the ocean, which over longer timescales can counteract some of the acidification and increase the capacity of the ocean to store carbon as carbonate sediments. The balance between these opposing effects varies in time and space. During the initial phases of rapid carbon dioxide input and rapid warming acidification and reduced carbonate saturation likely dominate, contributing to the observed platform disruption. As weathering catches up, conditions may gradually improve, but by then some communities have already declined. The isotopic composition of marine carbon in this interval supports the idea of a disturbed carbon cycle. Shifts toward lighter carbon isotope ratios in carbonates and organic matter imply large additions of isotopically light carbon, consistent with volcanic and methane sources. These changes coincide with faunal turnovers in several marine groups. Conodonts, a long-lived group of eel-like vertebrates with tooth elements that fossilize abundantly, show significant declines in diversity or temporary disappearances in some sections. Ammonoids, cephalopods with coiled external shells, experience extinctions and subsequent radiations. Some bryozoans and brachiopods, which form colonies, or shells from calcium carbonate, are reduced in number or replaced by taxa better adapted to altered conditions. The timing and magnitude of these changes vary among basins, but the general picture is of a marine biosphere under stress. A second mechanism by which the pluvial episode affects oceans is through changes in salinity and stratification. As rainfall intensifies and runoff increases the volume of fresh water entering coastal seas, and semi-enclosed basins grows. In some regions, especially near large river mouths and in epicontinental seas with restricted connections to the open ocean, this influx lowers surface salinity. Fresher water tends to be less dense than saltier water, and when it flows out over the surface of existing marine waters, it can create a stable stratification with a low salinity, relatively warm surface layer overlying denser, more saline deep water. Stratification inhibits vertical mixing, reducing the transfer of oxygen from the atmosphere into deeper layers. At the same time, increased nutrient input from land, including nitrogen and phosphorus compounds, liberated by intensified weathering and soil erosion, can stimulate primary productivity in surface waters. Phytoplankton and other producers bloom, fixing more carbon. When this organic matter dies and sinks, it is decomposed by bacteria, a process that consumes dissolved oxygen. In a stratified water column, the combination of reduced oxygen supply to depth and increased oxygen demand from decaying organic matter can drive intermediate and deep waters toward low oxygen or anoxic states. Geological evidence for such conditions in the Carnian includes the presence of finely laminated black shales in several marine basins, indicating deposition under low oxygen conditions where burrowing organisms are scarce or absent. Certain trace metal enrichments also point to anoxic or even sulfidic bottom waters. The distribution of these facies suggests that anoxia was not globally uniform, but extended across significant regions, especially in restricted basins and along some continental margins. For organisms adapted to well-oxygenated habitats such as many benthic invertebrates, these conditions represent a serious challenge. Those that can tolerate low oxygen, or that can migrate vertically or geographically, fare better. The pattern of survivors and victims in the fossil record offers indirect insight into the severity and extent of oxygen depletion. A third aspect of marine change during the pluvial episode involves the physical structure of coastlines. With enhanced runoff and sediment input, deltas prograde more rapidly, building seaward into basins. Estuaries fill with sediment. Shorelines become more dynamic with barrier systems and tidal flats, adjusting to increased river discharge and altered wave climates. In environments where carbonate-producing organisms once dominated, siliciclastic sediments now compete for space. This shift from carbonate to mixed or clastic-dominated systems alters local habitat structure and light availability, forcing reef builders and associated communities either to adapt or to retreat to more favourable locations. In some cases, reef systems reorganize around different builders or move along depth and latitude gradients, tracking zones with clearer water. The combination of carbonate platform crises stratification, induced anoxia and shoreline reconfiguration contributes to elevated extinction rates in marine faunas during the Carnian. It is not a single sharp crash like the end Permian event, but more of a prolonged interval of elevated stress and turnover. Some lines of evidence suggest that extinction rates remained high for hundreds of thousands of years, with recovery and diversification of new groups overlapping the tail of the disturbance. This extended nature complicates attempts to define a discrete marine extinction boundary, but it reinforces the idea that the pluvial episode represents a sustained perturbation rather than a brief anomaly. Within this framework, there are specific puzzles that continue to interest researchers. One concerns the apparent thinning of shells in some mollusks and other shelled organisms during the interval. Measurements on well-preserved fossils suggest that in certain localities shell walls are thinner and show more growth irregularities compared with earlier or later specimens of similar taxa. This could be a response to reduced carbonate availability, to physiological stress from temperature and salinity fluctuations, or to evolutionary changes in resource allocation under new ecological pressures. Another puzzle relates to the behavior of some groups that appear to thrive. While many carbonate platform formers decline, some taxa adapted to slightly deeper, cooler or more turbid environments expand. In regions where platforms drown or are eroded, deeper basin communities step in to occupy vacated ecological space. This pattern hints at a redistribution of ecological opportunity rather than a simple loss. It also mirrors in the marine realm the way some terrestrial groups take advantage of new wetland and forest habitats on land. The link between rainfall and ocean changes is thus not just a matter of extra freshwater. It involves a rebalancing of carbon nutrients and physical structure over large areas and long timescales. Volcanic gases initiate warming and a faster hydrological cycle. Enhanced rainfall and runoff alter chemical weathering, nutrient delivery and salinity. Ocean circulation responds changing patterns of upwelling and mixing. Ecosystems adjust with some lineages declining and others radiating. The Carnian oceans do not flood their basins in the sense of dramatically rising sea level, but the conditions within those basins change in fundamental ways. From a modern perspective, the evidence for this marine transformation is locked in details of limestone shales and fossil assemblages scattered across former margins of Pangaea. Each new section studied adds nuance. Some confirm the overall picture of stressed carbonate platforms and expanded anoxia. Others show more muted responses, reminding investigators that regional context matters. Reconciling these differences requires careful attention to local geography currents and connections to the open ocean. It also opens space for questions about how close the system came to a more severe marine crisis and what factors may have limited the extent of damage. Perhaps circulation patterns prevented anoxia from reaching the most open parts of the Panthalassa. Perhaps biological feedback, such as shifts in plankton communities, moderated some chemical extremes. The answers remain incomplete, but the broad outcome is clear under the influence of a prolonged interval of heavy rain and elevated greenhouse gases. Earth's oceans during the Carnian experience a period of reorganization that affects who lives where and under what conditions. While many familiar Triassic marine lineages persist, their distributions and relative abundances change, setting the stage for further evolutionary developments in later stages. As in the terrestrial realm, the disturbance does not simply reset the system, it nudges it onto a slightly different trajectory. With the marine context in place, attention can return to land where the same rains that feed, altered rivers and lakes also reshape plant communities and the large herbivores that depend on them. In these changes lie clues to why some long successful groups fade and why others, including lineages that will later dominate the Mesozoic, begin to rise. On land, the persistent rain of the Carnian pluvial episode does not only deepen channels and fill lakes, it filters through the fabric of ecosystems by altering which plants can grow, where how fast they can spread, and how reliable their water supply becomes. Over thousands of years, these changes in vegetation feed directly into the fortunes of the large herbivores that depend on them, and indirectly into the lives of the predators and scavengers that feed on those herbivores. The result is a gradual but significant rearrangement of terrestrial communities, in which some once abundant groups begin to wane, while others take advantage of new opportunities. Before the onset of the pluvial conditions, many Triassic landscapes, especially in low-latitude regions of Pangaea, are dominated by relatively open vegetation. Conifers and seed ferns stand in scattered groves or line river corridors. Between them, expanses of bare ground, low shrubs, and drought-tolerant plants fill the space. In such settings, large herbivores adapted to browse and graze across open or lightly wooded terrain can thrive. Among these are rhynchosaurs, robust reptiles with deep skulls, expanded jaws and dental batteries suited to processing tough plant material. Fossil assemblages from early Carnian formations show that rhynchosaurs can be extremely abundant, sometimes making up a large fraction of recorded vertebrate specimens. Their bones occur in multiple growth stages, indicating resident populations rather than rare visitors. Their success suggests that the vegetation mosaic favours their feeding style, perhaps dominated by certain seed ferns and other low to medium height plants that can endure seasonal dryness and recover between grazing episodes. Alongside the rhynchosaurs, dicynodonts occupy their own herbivorous niches. These synapsids, more closely related to mammals than to reptiles, often have tusks and beak-like mouths. They too have a long history extending back into the Permian. Through earlier crises, they have persisted adjusting their body forms and lifestyles to changing conditions. In the early Carnian, some desynodont lineages remain common in several regions, contributing significantly to the herbivore guild. Their feeding strategies, combining cropping of vegetation with efficient processing in the gut, are well suited to a range of plant communities. Other herbivores, including early relatives of later Ornithischian dinosaurs and various archosauromorphs, share space on these landscapes, but rhynchosaurs and desynodonts stand out in many deposits as major components. As the climate shifts into the pluvial mode, the structure of plant communities begins to change. Increased rainfall and more persistent soil moisture allow forests to expand. Areas that once supported only scattered trees in a largely open matrix now develop closed or semi-closed canopies. Shade-tolerant ferns and understory plants spread. Peat-forming wetlands emerge in low-lying basins dominated by dense stands of plants adapted to waterlogged soils. The composition of dominant flora also adjusts. Conifers and seed ferns diversify, and in some regions, new groups with different leaf and stem architectures become prominent. Pollen and spore records from Carnian and immediately post-Carnian sediments show shifts in relative abundances that track these plant reorganizations. For herbivores, these changes are not simply a matter of more food. They represent a different kind of foodscape. Plants that prosper under wetter, more shaded conditions may have different growth rates, tissue toughness, and chemical defenses than those that dominated the earlier, more open environments. Systems of roots and stems interact differently with soils that are frequently saturated. Some of the low-growing plants that rhynchosaurs relied on may decline in favor of taller canopy-forming species and ferns, whose distribution and accessibility differ. There is evidence that rhynchosaurs experience a marked decline over the course of the Carnian pluvial episode. In formations that span the interval, their remains become less frequent and eventually disappear in many regions. While the exact timing of their final disappearance is still refined as new data arrive, the broad pattern is clear: a group that was once locally abundant and ecologically important fades, and no later fossils unambiguously assignable to rhynchosaurs are known from post-Carnian stages. Several hypotheses have been proposed to explain this decline. One focuses on the vegetation change. If rhynchosaurs were specialized feeders on particular plant groups that did poorly under the new wetter conditions, their food base may have shrunk. Competition with other herbivores, such as those better adapted to browsing higher or selecting different plant parts, could then have further stressed rhynchosaur populations. Another hypothesis highlights the indirect effects of more frequent flooding and waterlogged soils on nesting sites, juvenile survival or disease dynamics. With more stagnant water and densely vegetated lowlands, parasite loads and pathogen transmission might have increased. It is difficult to test these ideas directly, but the coincidence of climate-driven plant reorganization and rhynchosaur decline encourages the view that the pluvial episode plays a significant role in their fate. Desynodonts also show a contraction in diversity and abundance around this time, though their pattern is somewhat more complex. Some lineages appear to persist beyond the peak of the pluvial interval, surviving into subsequent stages before disappearing. Their long evolutionary history and previous ability to adapt to different climates suggest a degree of resilience. However, they too eventually leave the record, and by the end of the Triassic, desynodonts are gone. Shifts in vegetation competition with emerging herbivore groups and broader environmental stresses from volcanically driven climate change likely all contribute. The exact weighting of these factors remains debated, but the outcome is that two herbivorous clades with deep roots in Permian and early Triassic ecosystems no longer dominate Carnian and post-Carnian landscapes. While these established herbivores face difficulties, other groups find the new conditions favorable. The expansion of forests and wetlands creates niches for animals capable of efficient movement in dense vegetation, of exploiting high foliage, or of feeding in and around aquatic environments. Early sauropodomorph dinosaurs, small to medium-sized at this stage, begin to appear more frequently in the fossil record. Initially, many of them are likely omnivorous or flexible in diet, but over time some lineages show adaptations consistent with more dedicated plant eating, such as changes in jaw mechanics and body proportions. Their bipedal or facultatively quadrupedal stance allows them to reach different feeding heights, and their relatively lightweight skeletons help them navigate complex terrain. Other archosaurs, including etosaurs, develop body plans suited to herbivory in forested or wetland settings. Etosaurs are heavily armoured with broad bodies and pig-like snouts. Their teeth and jaw structures indicate a diet rich in plant material, and their limb proportions suggest a terrestrial lifestyle. In the context of widespread wetlands and conifer-dominated forests, etosaurs may have grazed or rooted through soft ground in search of roots, shoots, and fallen plant matter. Their armour would have offered protection in environments where large predators still roam. The success of such groups is reflected in their increasing diversity and geographic range in post-Carnian formations. Smaller herbivores and omnivores also respond to the changing plant world. The spread of understory vegetation and the complex vertical structure of forests provide new opportunities for climbing, gliding, or burrowing forms, including early relatives of lizards and other lepidosaurs. Even without detailed fossils of every lineage, the overall trend from more open, seasonally dry landscapes to more closed, humid ones implies a wholesale reorganization of community structure. In the midst of these shifts, the role of the Carnian pluvial episode as a selective filter becomes apparent. The episode does not erase all herbivores or favour all forest dwellers. Instead, it modifies the operating conditions under which existing lineages must function. Those that can adjust their diets move into new habitats, or take advantage of wetter soils and denser plant cover may expand. Those tied closely to a particular combination of plant types and surface conditions may contract. The rain itself does not choose. The combination of water heat and changing vegetation shapes the probabilities of survival and success. There is also an important temporal aspect. The wet interval lasts long enough for evolutionary responses to arise. Lineages are not simply displaced by short-term weather anomalies. They're given or challenged with environmental trends that persist over many generations. Traits that confer advantages under these trends can become fixed and elaborated. When the climate later swings back toward more arid conditions, the descendants of lineages that adapted during the pluvial episode carry with them the imprint of that time, influencing how they interact with the new or returning environments. This contributes to a sense in which the Carnian pluvial episode acts as an ecological and evolutionary hinge. Before it, rhynchosaurs and dicynodonts are dominant elements of many herbivore guilds and forests, though present occupy more limited extents. During it, forests and wetlands expand and some new herbivore forms gain footholds. After it, the dominant composition of herbivore communities in many regions looks different, with early dinosaurs and archosaur herbivores more prominent and some older lineages absent. The precise boundaries between these phases vary regionally, and in some areas the transitions are more gradual than in others. This variability is itself informative, indicating that local geography, plant diversity, and community interactions modulate the response to global climate forcing. One of the outstanding questions concerns how tightly herbivore turnover is linked to specific plant changes. Pollen and macrofossil records show broad shifts, but correlation with vertebrate assemblages is often limited by differences in preservation and sampling. Detailed studies of basins where both records are strong may help clarify whether the decline of groups like rhynchosaurs coincides with lags behind or precedes particular floral transitions. Such timing relationships would shed light on whether plant changes are the primary driver of herbivore decline, a contributing factor, or more of a parallel response to shared climate stresses? Another question involves the role of geographic refuges. If some areas retained more open, seasonally dry vegetation even during the pluvial episode, they might have provided havens for herbivores specialized on such habitats. The patchiness of fossil discoveries leaves open the possibility that some lineages persisted longer in such refuges than current records indicate. The eventual absence of their fossils in later stages shows that any refuge role was temporary, but the details of how and where they held on and for how long remain to be discovered. Through these uncertainties, one pattern persists. The Carnian pluvial episode does not simply add water to a static system. It converts a set of landscapes and ecological relationships into another with cascading consequences. Forests and wetlands become more extensive and structurally complex. Herbivore guilds lose some long-standing members and gain others. Predators and scavengers must either follow these changes or succumb to them. The rain acts on rock, soil, and plant communities simultaneously, and the combined effect is a redefinition of who eats what and where. This redefinition sets the stage for the rise of certain archosaur groups, including dinosaurs and crocodile relatives, to ecological prominence. As the climate system eventually relaxes and some regions return to more arid states, these groups will carry forward their adaptations to the wet interval, influencing how they exploit new or returning habitats. The next phase of the story follows these emergent winners tracking how a lineage that begins as small, lightly built animals in a humid, flooded world eventually becomes a central component of Mesozoic ecosystems. As the Carnian pluvial episode reshapes forests, floodplains, and wetlands, it also alters the competitive landscape for vertebrate predators and agile omnivores. In this changed world, early dinosaurs and their close relatives find new opportunities. They do not yet dominate all ecosystems, but their presence becomes more frequent and more varied, and their anatomical experiments hint at future success. At the same time, other archosaurs, including the ancestors of crocodiles and heavily armoured herbivores, also expand. The prolonged wet interval thus coincides with a reorganization of the archosaur radiation, in which different lineages explore the possibilities offered by a more humid, structurally complex environment. Before and during the early stages of the pluvial episode, dinosaurs are small and relatively rare components of terrestrial faunas. In formations such as the Santa Maria succession of what is now southern Brazil, early dinosaurs appear alongside numerous other reptiles and synapsids. Staurikosaurus, a lightly built bipedal carnivore, measures only a few meters in length. Its limbs are slender, its tail long, and counterbalancing its skull equipped with sharp serrated teeth, suitable for hunting small to medium-sized vertebrates. Buriolestes, another early form, shows features linking it to sauropodomorphs, the lineage that will later give rise to giant long-necked herbivores, yet its teeth and jaw confirm a diet that is still at least partly carnivorous or omnivorous. These animals are not yet the large specialized herbivores or apex predators familiar from later periods. They share their environments with a variety of non-dinosaurian archosaurs, including forms that closely resemble dinosaurs in posture and limb structure, but fall just outside the true dinosaur clade. These dinosauromorphs are often even smaller agile insectivores or small vertebrate hunters that move on two legs through low vegetation or along the margins of water bodies. Their presence indicates that the basic body plan of an upright bipedal active reptile is being explored in multiple related lineages. In parallel, other archosaurs occupy larger-bodied roles. Rauisuchians, large robust predators with massive heads and strong limbs, stand near the top of many food chains. Some are quadrupedal with pillar-like limbs under the body, others may have moved with a semi-erect posture. Their skulls bear powerful jaws and teeth, adapted for seizing and dismembering sizable prey. Phytosaurs elongate semi-aquatic predators with long snouts and nostrils positioned near the eyes, patrol rivers and lakes, taking fish and terrestrial animals that approach the water. Etosaurs, heavily armoured herbivores with broad flat bodies and spiked shoulder regions, browse or dig in the soil for plant material. Early crocodilomorphs, smaller and more gracile than modern crocodiles, move on land with agility, some perhaps taking small prey in more open or lightly wooded areas. In the context of the Carnian pluvial episode, these groups do not all respond identically. The expansion of rivers, lakes and wetlands clearly benefits semi-aquatic and amphibious forms. Phytosaurs, for instance, find an extended network of suitable habitat. Their fossils become more geographically widespread and more morphologically diverse in post-Carnian stages, suggesting that they diversify in response to the proliferation of aquatic environments. Etosaurs may take advantage of the expanded moist floodplains and conifer-dominated forests rooting through soft ground and feeding on abundant plant matter. These patterns are consistent with the idea that rain-driven habitat expansion creates ecological space for certain archosaurs to radiate. For early dinosaurs, the advantages may be more subtle, but still important. The more complex vertical and horizontal structure of vegetation in humid forests, combined with more frequent disturbances such as floods and tree falls, produces a patchwork of microhabitats. Small bipedal animals with good maneuverability and relatively high aerobic capacity are well suited to exploiting such mosaics. They can move quickly between open patches and cover climb low obstacles, and adjust their foraging routes as rivers shift and new clearings form. Their limb anatomy, with an erect posture and a strong muscular tail, permits efficient locomotion over long distances and asset in landscapes where resources are distributed in dynamic patterns. In formations such as the Ischigualasto succession of modern Argentina, deposited near the end of the Carnian, and into the succeeding Norian stage, the rise of dinosaurs becomes clearer. There, faunas contain multiple dinosaur species alongside other archosaurs and synapsids. Herrerasaurus, a large carnivorous dinosaur, reaches lengths of several meters and occupies one of the top predatory roles. Its skull, with large serrated teeth and strong jaw muscles, indicates a capacity to tackle substantial prey, including other reptiles. At the same time, smaller forms such as Eoraptor and Eodromeus appear representing basal members of the main dinosaur lineages. Eoraptor shows a mixture of traits that suggest an omnivorous diet, while Eodromeus is more clearly adapted to carnivory. Sauropodomorphs such as Panphagia and other related forms also occur, hinting at the early experimentation that will lead to large herbivorous dinosaurs in later periods. The key point is that in these deposits, dinosaurs are no longer rare curiosities. They make up a significant fraction of the vertebrate assemblage, and their diversity is higher than in earlier Carnian formations. This increase in abundance and variety follows in time the interval of intense rainfall and vegetation reorganization associated with the pluvial episode. The correlation does not prove direct causation, but it supports the view that the environmental changes of the pluvial interval play a facilitating role in the dinosaur radiation. One way to conceptualize this role is as a shift in the background field of environments and competitors. Before the pluvial episode, archosaur predators such as Rauisuchians and large non-dinosaurian forms occupy many of the apex and mesopredator roles. Herbivorous niches are filled by rhynchosaurs, dicynodonts, and various other reptilian herbivores. Dinosaurs and their close relatives are small generalist animals operating largely in the shadow of these established clades. The pluvial episode disrupts this pattern not by eliminating all competitors at once, but by incrementally changing habitat structure, food availability, and mortality regimes. Some established herbivores decline as their preferred vegetation and soil conditions become less common. Others face increased disease or reproductive challenges in flooded or waterlogged environments. On the predatory side, changes in prey distributions and habitat structure alter hunting efficiency for large quadrupedal predators. Semi-aquatic predators thrive, but their specialization ties them closely to water bodies. Into this evolving matrix step the dinosaurs and certain crocodilomorphs. Their body plans confer a specific set of advantages under the new conditions. An erect gait with limbs positioned under the body reduces the energy cost of locomotion compared with sprawling postures, particularly over longer distances. Hollow or partially hollow limb bones in many dinosaur lineages reduce weight without sacrificing strength. Their respiratory system, though not fully understood in early forms, likely evolves toward increased efficiency, allowing sustained activity in warm, low-elevation environments. For small to medium-sized omnivores and carnivores navigating a humid, patchy landscape with frequent disturbances, these traits can translate into higher foraging efficiency, improved predator avoidance, or more effective hunting. Crocodilomorphs at this time are mostly small terrestrial or semi-terrestrial animals, some with cursorial adaptations. They too possess erect or semi-erect limb postures in many cases, and their skulls and teeth show a variety of feeding strategies. In some ecosystems, they may have competed directly with small dinosaurs for similar prey. The coexistence of these groups suggests that the ecological space opened by the pluvial episode was not monopolized by a single lineage, but rather partitioned among several. Over longer timescales, however, the dinosaur branch proves particularly successful, especially as some lineages shift toward larger body sizes and more specialized diets. Another aspect of the pluvial episode that may influence archosaur evolution is the pattern of disturbance. Frequent flooding channel avulsions and treefall events continually reshape local patches of habitat. In such a setting, lineages that can disperse effectively and colonize newly available areas quickly have an advantage. Small body size and high reproductive rates can facilitate this, as can flexible diets. Early dinosaurs, many of which are small and possibly omnivorous, fit this profile. Their ability to exploit both animal and plant resources to feed at different heights and to move efficiently may have allowed them to expand rapidly into disturbed habitats, left vacant or underused by less mobile or less flexible species. Meanwhile, the expansion of phytosaurs and other semi-aquatic predators underlines that the pluvial episode is not simply a time of opportunity for dinosaurs alone. In many river and lake systems, phytosaurs become important apex predators, reaching large body sizes and broad geographic distributions. Their success illustrates that the same climatic forces can promote different outcomes in different lineages, depending on pre-existing adaptations. Etosaurs likewise show increased diversity with various armor patterns and body proportions. Their broad, heavy bodies and strong limbs suit them to a life of foraging in forest floors and floodplains, taking advantage of the abundant plant material. Their presence in many Carnian and Norian deposits indicates that the role of large herbivore is now shared among multiple archosaur clades, including early sauropodomorphs and other dinosaurian herbivores. Rauisuchians remain significant predators through much of the late Triassic, but there are hints that their dominance begins to wane as the period progresses. Some large forms appear in post-Carnian and Norian deposits, including very large species that reach considerable lengths and masses. Yet by the end of the Triassic, Rauisuchians as a group disappear, whereas dinosaurs and crocodilomorphs persist and expand. The reasons for this eventual divergence of fortunes likely involve factors beyond the Carnian pluvial episode alone, including later volcanic events and additional climatic perturbations. However, the pluvial episode marks an early stage in the process by which dinosaurs move from minor components of faunas to major players. From a modern vantage point, one of the striking aspects of this story is the way deep earth processes and surface climate anomalies intersect with the anatomy and behavior of specific lineages. The same flood basalts that inject greenhouse gases into the atmosphere and trigger prolonged wet conditions also create indirectly the environmental matrix in which the dinosaur body plan proves advantageous. This does not imply any directed outcome. It is a contingency arising from the intersection of one set of physical changes with one set of biological options. Nevertheless, the pattern recurs often enough in Earth history to invite reflection. Large igneous provinces and associated climate excursions are repeatedly linked with pulses of extinction and radiation. In the Carnian, the radiation favours particular archosaurs and alters the balance between synapsids and reptiles on land. The details of timing and cause remain topics of active research. Investigators work to refine dates to understand how many distinct pulses of volcanic activity occurred and to compare these with the fine structure of faunal changes. They also seek to clarify the relationships among early dinosaur lineages and between dinosaurs and other archosaurs to determine which traits evolved before, during or after the pluvial episode. Each new fossil discovery, each improved age constraint adds resolution. Yet even as the picture sharpens, some aspects stay open. It is not fully known how strongly the wet conditions themselves independent of temperature changes and other factors influence evolutionary trajectories. It is also unclear how variable the dinosaur response is across different regions. In some basins they may have remained minor elements for longer, while in others they appear to rise rapidly. These uncertainties leave room for further work, and for the possibility that the relationship between the era of almost continuous rain and the ascendance of dinosaurs is more complex than a simple cause and effect. Still, the association is robust enough that the Carnian pluvial episode can be seen as part of the prelude to the Mesozoic world, dominated in many ecosystems by dinosaurs and their close relatives. The next step in the narrative broadens the view further, comparing this episode with other times in Earth history when large volcanic provinces' climate perturbations and evolutionary shifts have coincided. In these comparisons, patterns begin to emerge that hint at a deeper regularity in how planets couple their internal heat and their surface biospheres. When the Carnian pluvial episode is viewed on its own, it appears as a distinctive anomaly in an otherwise relatively stable interval of the Triassic. Rainfall intensifies soils and sediments, register prolonged wetness, and ecosystems rearrange. Yet when it is placed alongside other events in Earth history that involve large igneous provinces and major climate perturbations, patterns begin to emerge. These patterns do not turn the Carnian episode into a simple repetition of other crises, but they suggest that certain combinations of processes recur when the planet's interior and surface systems interact in particular ways. One of the clearest comparisons lies earlier in time at the boundary between the Permian and the Triassic. Their much larger flood basalt event in what is now Siberia coincides with the most severe mass extinction known. Vast volumes of lava erupted over a relatively short geological interval, accompanied by enormous releases of carbon dioxide and other gases. Geochemical records show strong rapid shifts in carbon isotopes, indicating large additions of isotopically light carbon. Oxygen isotopes and other proxies point to marked warming. Evidence for widespread ocean anoxia is abundant, with black shales deposited across many basins. On land, plant communities are disrupted, soils erode, and many lineages disappear. The scale and speed of these changes far exceed those of the Carnian pluvial episode. However, the underlying structure is similar. A large igneous province injects greenhouse gases, the climate warms, the hydrological cycle accelerates, and environmental stresses propagate through oceans and continents. The outcomes differ in magnitude, but the sequence follows a comparable logic. Later in the Triassic, near its close, another large igneous province forms as the supercontinent begins to rift apart. In what will become the margins of the Atlantic Ocean, extensive basaltic volcanism again coincides with faunal turnover and climate change. This time, the associated extinction event affects many marine and terrestrial groups, including some large archosaur predators, while dinosaurs and other lineages persist and expand into the Jurassic. Carbon isotope records and sedimentary evidence again point to pulses of greenhouse gas release and altered ocean chemistry. While the specific arrangements of continents, seas, and ecosystems differ from those of the Carnian, the combination of flood basalts warming and biotic reorganization recurs. Moving still further forward in time, the end of the Cretaceous provides another example, though its causality is more complex. A large bolide impact in what is now the Yucatan Peninsula injects dust and aerosols into the atmosphere, triggering short-term cooling and reduced sunlight. At roughly the same time, though, likely over a longer interval, extensive basaltic eruptions occur in the region now known as the Deccan Traps. These eruptions add substantial greenhouse gases to the atmosphere. Untangling the relative contributions of impact and volcanism to the extinction that removes non-avian dinosaurs and many marine groups is challenging, but the conjunction of large igneous activity, climate change, and biotic turnover appears again. In this context, the Carnian pluvial episode occupies an intermediate position. It is associated with a large igneous province that is smaller than the Siberian or Deccan provinces, and the climatic and biological consequences, while significant, fall short of the most catastrophic events. There is no global collapse of ecosystems, but there is a noticeable increase in extinction rates, a reorganization of marine and terrestrial communities, and a shift in dominant groups. The marine carbonate platform crisis, the expansion of anoxic conditions in some basins, the decline of rhynchosaurs and some dicynodonts, and the rise of certain archosaurs all mark the Carnian interval as a time when the biosphere's trajectory is deflected. The recurrence of this broad pattern raises two related questions. The first is mechanical. Why do large igneous provinces so often coincide with climatic and biological upheavals? The second is statistical. Given the frequency of igneous events over geological time, is the alignment with major changes in life an unlikely coincidence or an expected outcome of how the Earth system operates? The mechanical aspects are increasingly understood in outline. Large igneous provinces represent efficient pathways for mantle heat and volatiles to reach the surface. When they erupt, they can release carbon dioxide and other greenhouse gases at rates that exceed the capacity of natural sinks to absorb them on short timescales. The result is an abrupt increase in atmospheric carbon warming and changes in the hydrological cycle. Warmer temperatures can destabilize methane-bearing sediments, adding more greenhouse gases. Changes in rainfall and weathering alter nutrient supply and sediment delivery to the oceans, influencing marine productivity and oxygen levels. Sulfur gases can produce short-term cooling and acid rain, adding further stress. These processes operate regardless of the precise geographic location of the province. What matters is the rate, duration, and composition of volatile release, and how these match the sensitivity of the contemporary climate and biosphere. The Carnian pluvial episode fits this framework with some particularities. The position of Pangaea concentrates land in one large mass, amplifying monsoonal responses to warming. The existing lack of permanent ice limits certain feedbacks, but also means that modest additional warming can significantly increase evaporation. The hydrological response manifests as broader and longer wet seasons in many regions rather than as major ice melt. The biosphere at this time is in a phase of recovery and diversification after earlier crises, with new clades such as early dinosaurs and advanced archosaurs already present but not yet dominant. When the pluvial episode arrives, it interacts with this evolving community, shaping which lineages expand. The statistical question is more difficult. On long timescales, plate tectonics and mantle convection produce many igneous events. Not all are associated with major environmental change. Some large igneous provinces appear in the geological record without clear evidence of global extinctions or severe climatic anomalies. This indicates that the presence of a large igneous province is a necessary but not sufficient condition for a major perturbation. Other factors, such as the background climate state, the composition of sediments intruded by magma, and the configuration of continents and oceans influence the ultimate impact. The Carnian episode again provides an example. Its volcanism occurs in a world without large ice sheets, with a supercontinent configuration, and with extensive organic rich sediments in some basins. These conditions favour efficient translation of igneous activity into greenhouse forcing and hydrological intensification, but they do not obligatorily produce a mass extinction on the scale of the Permian event. Instead, the outcome is a moderate level of extinction and a significant rebalancing of ecosystems. From this perspective, the Carnian pluvial episode may be viewed as one realization of a broader template, a convergence of internal heat release and surface sensitivity that yields a specific pattern of change. The template can be sketched in general terms. First, volcanic activity on a large scale injects greenhouse gases and in some cases other climatic agents into the atmosphere. Second, the climate warms and the hydrological cycle accelerates with regionally varied effects on rainfall and evaporation. Third, surface processes respond, soils develop or erode differently, rivers and lakes reorganize, and chemical weathering rates adjust. Fourth, oceans experience changes in temperature stratification and chemistry affecting carbonate saturation and oxygen levels. Fifth, ecosystems on land and in the sea face new combinations of temperature-water availability and habitat structure. Some lineages decline, others expand, and evolutionary innovations are filtered by the new conditions. Finally, as volcanic activity wanes and feedback such as enhanced weathering draw down carbon, the climate gradually relaxes toward a new quasi-stable state. The specific expression of each stage depends on the initial conditions. In the Permian, heavy carbon loading and a different configuration of continents result in extreme warming and widespread anoxia, driving a mass extinction. In the Carnian, the perturbation is substantial, but smaller, leading to a more selective, though still important, restructuring. At the end of the Triassic, as Pangaea begins to break apart, the combination of volcanism and rifting again drives environmental change, this time coinciding with another significant extinction. The recurring motif is that episodes of intense volcanic outgassing at the surface of a convecting planet frequently test the resilience of the biosphere. The existence of such a motif does not imply any directional trend. Some events, like the Carnian pluvial episode, appear to favour the rise of groups that will later become ecologically prominent. Others remove dominant lineages and open space for entirely new solutions. Over hundreds of millions of years, this interplay between internal geology and surface life contributes to the uneven, stepwise character of evolution, in which long intervals of relative stability are punctuated by episodes of accelerated turnover and innovation. In this sense, the Carnian episode serves as both an example and a reminder. It shows that significant ecological and evolutionary shifts can occur in association with climate changes that are less extreme than the very largest catastrophes. It also emphasizes that rain, a familiar and seemingly gentle component of climate, can play a central role in such shifts when its timing and intensity are altered on global scales. Intense rainfall links the carbon released by deep magmas to the fates of shallow-rooted plants and mobile animals. The recognition of these recurring patterns has practical implications for how the behavior of planetary climates is conceptualized. When astronomers and planetary scientists consider the climates of rocky planets elsewhere, they note not only the amount of starlight and the composition of atmospheres, but also the potential for internal heat and volcanism to reshape climates episodically. The Carnian pluvial episode, together with other igneous-linked events, illustrates that a planet can spend long periods in relatively stable modes, punctuated by intervals in which internal and surface processes temporarily align to produce unusual combinations of heat, water, and chemistry. Whether such episodes are more common on planets with supercontinents or on those with different continental arrangements remains an open question. Each comparison between Earth's own episodes adds a piece of information. Even on Earth, many details are unresolved: the precise rates of gas release, the spatial patterns of rainfall, the feedbacks involving clouds and vegetation, and the fine timing of biotic responses. The existence of a broad template connecting volcanism, carbon, and water is supported by multiple lines of evidence, but the range of possible outcomes under that template remains large. The Carnian pluvial episode occupies one point in that range, sitting between more moderate and more extreme events. Its study therefore contributes not only to understanding a particular interval of prolonged rain in the Triassic, but also to refining the general picture of how a geologically active planet cycles through episodes of fire and flood, each leaving lasting traces in rock and life. In the deep past, the Carnian pluvial episode unfolds without observers, guided only by the interaction of mantle heat, plate motions, oceans, atmosphere, and evolving life. In the present, it exists as an inferred pattern assembled from scattered clues. There is a distance between those two realities, yet attempts to bridge it, a part of a broader effort to understand how planets behave when internal energy and surface water interact. In that sense, the long-vanished rains of the Carnian have relevance beyond their time, offering a reference point for thinking about Earth's own future climate shifts and about the climates of other worlds. On Earth today, observations from satellites, ocean buoys, and ground stations show that as greenhouse gases increase, the global water cycle responds. Warmer air holds more moisture, leading to heavier rainfall events in many regions. Some areas experience more frequent intense storms and floods, others endure longer dry spells punctuated by violent precipitation. The basic physical principles at work are the same as those inferred for the Triassic. Increased greenhouse forcing raises temperatures, enhances evaporation, and allows the atmosphere to carry more water vapor. When that vapor condenses, the release of latent heat further fuels circulation. The details of modern patterns differ, because continents are arranged differently, ice sheets are present, and the timescales involved are much shorter. But the underlying relationship between warming and a more energetic hydrological cycle is shared. The Carnian pluvial episode, reconstructed from rock, provides an example of how far such a relationship can go when sustained over hundreds of thousands to millions of years. In that episode, the result is not only more frequent heavy rain, but a lasting reorganization of landscapes and ecosystems. The comparison does not imply that modern trends will reproduce a Triassic-style world. The rates of change, the starting conditions, and the human role all differ. Instead, the ancient episode acts as an extended natural experiment that demonstrates the capacity of a planetary water cycle to amplify and propagate a greenhouse perturbation. It shows that under certain conditions, rain can become a primary agent of change, reshaping both physical geography and biological communities. For Earth's long-term future, other variables will come into play, including the slow drift of continents, changes in solar luminosity, and the eventual decline of plate tectonics. Yet the principle that atmospheric composition and water cycling are closely linked is likely to remain important. The Carnian record reminds investigators that when contemplating climate trajectories over geological scales, episodes of intensified rain and associated flooding are not anomalies, but part of the range of behaviours available to a warm, water-rich planet with active volcanism. Beyond Earth telescopes now detect planets around other stars in large numbers. For a subset of these, limited information about size, mass, and orbital distance is available. For a much smaller subset, there are hints of atmospheric composition. Direct knowledge of their surface conditions is absent, but models of planetary climates can fill in some possibilities. In these models, planets with dense atmospheres and surface water often show strong coupling between greenhouse gas levels and the strength of their hydrological cycles. On a world with land masses large enough to support monsoons, increased greenhouse forcing could lead to intensified rainfall, expanded humid regions and changes in ocean stratification, much as inferred for Pangaea during the Carnian. Whether any known exoplanet is currently in a state analogous to a pluvial episode is unknown, but the conceptual framework developed from Earth's history informs the search. For instance, if future missions obtain spectra of exoplanet atmospheres with signatures of abundant water vapour and variable cloud cover, interpreted alongside markers of volcanic gases. One possible reading is that the planet experiences significant hydrological activity modulated by internal heat. If its continents, if present, are arranged in a way that concentrates land in a single large mass, models would predict strong seasonal and possibly multimillennial variations in rainfall. While direct confirmation is far beyond current capabilities, Earth's record of episodes like the Carnian offers scenarios to compare against any eventual data. An observer looking down on Triassic Earth from above during the Carnian pluvial episode would see differences from earlier times that might be detectable in principle from afar. Cloud belts over Pangaea would appear broader and more persistent, especially in low to mid-latitudes. Large inland lakes would reflect light differently from surrounding land, and the extent of vegetated moist ground might alter the planet's overall reflectivity. If instruments could resolve spectral features of vegetation pigments, they might see an expansion of forest-like signals into regions formerly more barren. These are the kinds of integrated responses that Earth's climate and biosphere produce when the hydrological cycle intensifies. They serve as qualitative templates for interpreting distant unresolved worlds. Within Earth science itself, the Carnian episode continues to pose specific unresolved questions. One concerns the exact pacing of events. Did the main phase of intense rainfall occur in a few relatively sharp pulses separated by quieter intervals, or was it a more uniform plateau of wetness with modulations, high-resolution sedimentary records perhaps, with annual or seasonal layering in lake deposits, could offer insight, but such archives from the Carnian are rare and often incomplete. Another question involves the spatial pattern of wet and dry zones. Reconstruction suggests that while many regions became more humid, some interiors remained or became more arid. The precise boundaries between these regimes and their movement over time under changing circulation patterns remain topics for refinement. Climate models can map out possible arrangements, but they depend on assumptions about topography and atmospheric composition that carry uncertainties. A third area of inquiry focuses on biological responses in detail. The broad outlines of rhynchosaur decline, desynodont contraction, etosaur and phytosaur expansion, and dinosaur diversification are established, but the mechanisms linking these patterns to climate and vegetation changes are only partly understood. Were plant community shifts the primary drivers of herbivore turnover, or did disease predation and reproductive strategies play equally important roles? How did changes in flood frequency and wetland extent alter nesting success or juvenile survival for different groups? Answers to such questions will likely come from integrated studies of trace fossils, bone histology, and fine-scale stratigraphy in well-dated sections. Yet some degree of uncertainty is inherent given the fragmentary nature of the record. The persistence of these open questions underscores that the Carnian pluvial episode, while better characterized now than in earlier decades, is still an active research frontier. New discoveries can adjust timelines or alter interpretations. A fossil assemblage from a previously unsampled basin might show a different trajectory of herbivore change. A refined radiometric date could tighten or shift the overlap between volcanic pulses and sedimentary signatures. An improved climate model with updated boundary conditions could alter expectations for rainfall distribution. Each such refinement narrows the space of plausible scenarios without completely eliminating ambiguity. That residual ambiguity is not purely a limitation. It also reflects a basic property of deep time reconstructions. They deal with systems that are complex and only partially observable. Multiple models can fit the existing data to varying degrees, and distinguishing among them requires both new evidence and careful reasoning. The Carnian episode sits in this balance with a core narrative supported by multiple lines of evidence, and with many details still adjustable at the edges. The core narrative is that during a span of the late Triassic, Earth's climate shifted into a state characterized by heightened rainfall and humidity over large areas driven in significant part by greenhouse gases released from extensive volcanism. This shift altered soils, rivers, lakes, and seas, imposed stress on some organisms, and opened opportunities for others. When the forcing eased, and feedbacks drew the system back toward a drier equilibrium, the planet did not return to its previous configuration. Landscapes had been reworked, and the living component had resorted into new arrangements. In the rock record, this history is encoded in changes of colour, grain size, chemical ratios, and fossil composition. In conceptual space, it stands as one of several examples of how a planet's internal and external processes can align for a time to produce conditions that are neither fully stable nor fully catastrophic, but that nonetheless leave lasting marks. For anyone studying planetary climates and biospheres, this kind of episode is a reminder that the range of possible states is wide and that transitions among them can be driven by processes that originate deep below the surface. Volcanic gas release hydrological intensification and ecological response form a sequence that can repeat under different configurations and with different outcomes. The Carnian pluvial episode is one realization of that sequence. Others are more severe, others milder, some perhaps yet unrecognized in the fossil record. On Earth, the evidence of the Carnian rains is scattered but sufficient to reconstruct their broad outline. On other worlds, such episodes may occur without any record accessible to distant observers. The recognition that they are possible, however, shapes expectations. It suggests that planets with the right combination of internal heat, surface water, and atmospheric composition may experience their own eras when rain becomes unusually persistent, when rivers carve more deeply, and when life, if present, adjusts to a climate that is briefly on geological scales tilted toward flood rather than drought. The precise frequency and character of such eras on Earth and elsewhere remain open questions.